The Swiss Alps rise more than 2,000 meters above sea level at the Gotthard Massif. A train trying to cross them faces a simple, brutal arithmetic problem. The tunnel through the summit sits at 1,151 meters, but the cities on either side sit hundreds of meters lower. That gap had to be closed somehow. And the answer the engineers chose in the 1870s was not a longer tunnel or a steeper track. It was a spiral, a loop drilled entirely inside the mountain itself, carrying a train back on its own path just to gain altitude. 7 of those spirals are built into the Gotthard Railway. Most passengers riding between Zürich and Milan have no idea they exist. To understand why the spirals were necessary, you have to understand what the engineers were actually building. The Gotthard Railway was not a local line. From the moment it was conceived, it was designed as a trunk route, connecting northern and southern Europe, part of the corridor that would eventually link Rotterdam to Genoa. Construction started in 1872. The full line opened in 1882. That 10-year window included the completion of the Gotthard Tunnel itself, a 15-kilometer bore through the heart of the Massif, connecting Gotthard in the north to Airolo in the south. When it opened, it was the longest railway tunnel in the world. But finishing the tunnel only solved half the problem. A railway tunnel does not sit at the top of a mountain. It sits inside it, near the base of the summit zone. The Gotthard Tunnel's northern portal at Gotthard is already at 106 meters above sea level. The southern portal near Airolo is at 1,142 meters. Those numbers sound high, and they are, but the cities the line needed to connect were far below. Bellinzona on the southern approach sits at just 241 meters. The descent from the tunnel mouth to the lowlands covers roughly 900 vertical meters across a horizontal distance the terrain makes brutally short. Standard railway practice at the time allowed for gradients of around 26 to 27 parts per thousand on the Gotthard route, roughly a 2.6% grade. That is already steep for a heavily loaded freight train. Go steeper, and the locomotives of the era could not pull the loads required on an international freight corridor. Go shallower, and you need far more horizontal distance than the valleys actually provide. This is the engineering trap the designers faced. The valley floors descend too fast. The ridge walls close in too quickly. There is simply not enough lateral room to lay track in a straight or gently curving descent without either exceeding a workable gradient or carving through terrain that pushes back with millions of tons of rock. Every meter of altitude you need to lose requires a corresponding length of track to lose it safely, and the mountain was not offering that length on a straight line. The solution was geometrically elegant and visually strange. If you cannot extend the track horizontally because the valley runs out, you extend it by looping. A spiral tunnel takes a train through a full 360-degree curve inside the mountain, bringing it out at a lower elevation on the same hillside it entered. The train travels farther, the gradient stays within limits, and the passenger looking out the window sees only rock face and then open valley again, often confused about which direction they are now facing. The Gotthard line uses 7 of these spiral tunnels across its mountain approaches. On the southern side, the descent from Airolo toward Biasca involves the most dramatic sequence. The line drops through a series of looping tunnels and viaducts, reversing direction multiple times while threading through the valleys of the Ticino. Each spiral adds track length without adding horizontal distance along the valley floor. Each loop is a way of paying down the altitude debt that the mountains imposed. What makes this harder to visualize than it sounds is the three-dimensional geometry involved. From above, a spiral tunnel looks like a circle or oval drilled through a ridge. In cross-section, it is a helix. The track enters at one elevation and exits at another, having completed a full turn. When you are inside one as a passenger, you feel a continuous curve. You might notice the train seems to be turning for an unusually long time. You might catch a glimpse of the same valley from what feels like the wrong angle. Then the tunnel ends, and you are lower than you were, on what appears to be the same hillside, facing approximately the same direction you started. The line also has 36 tunnels in total, with a combined length of more than 31 kilometers. The spirals are the most structurally inventive of these, but the density of tunneling across the whole route tells the same story. The Alps did not allow a straightforward line, and the engineers of the 1870s and 1880s refused to let gradient limits become a ceiling on what the railway could carry. That refusal came at a cost. The approaches to the Gotthard Tunnel, the winding mountain sections with their spirals, viaducts, and tight curves, imposed permanent speed limits on the line. A freight train navigating a spiral tunnel cannot move quickly. The curves restrict velocity. The gradient demands careful braking on the descent and sustained power on the climb. By the late 20th century, the Gotthard Railway was operating near the limits of its capacity, and the geometry that had made it possible in 1882 had become the constraint holding it back in an era of high-speed rail and containerized freight. The line has 36 tunnels totaling more than 31 kilometers, and even with that infrastructure already in place, it was not enough. Traffic demand on the Rotterdam-Basel-Genoa corridor had grown beyond what a winding mountain railway could absorb. Freight was backing up. Schedules were constrained by the physics of negotiating tight spiral geometry under load. The 19th century solution was straining under 21st century demand. That tension drove one of the most consequential infrastructure decisions in Swiss history. In 1992, 64% of Swiss voters approved the new railway link through the Alps project. The centerpiece was a new tunnel, built not at mountain height, but at the base of the Alps entirely. The Gotthard Base Tunnel, completed in 2016, runs 57 kilometers at a nearly flat grade, bypassing the spirals, the altitude, and the 19th century geometry altogether. It is the longest railway tunnel in the world and the deepest traffic tunnel ever built. Its primary purpose was to shift freight from trucks to trains, reducing both environmental damage and road casualties on alpine routes. The original Gotthard Railway, spirals and all, did not disappear. It still operates. Regional services use it. The mountain route remains a functioning line, and the spirals that puzzled passengers for over a century are still there, still working, still solving the same altitude problem they were designed to solve in the 1870s. But the existence of the base tunnel clarifies what the spirals always were: not a permanent solution, but the most sophisticated answer a 19th century engineering team could devise for a problem that the terrain made genuinely hard. They added track length to buy altitude. They drilled full circles through mountain rock to stay within gradient limits. They built a line that connected two continents through terrain that had no easy path, and they kept it running for well over 100 years before something better could be built underneath it. The Gotthard Base Tunnel made the crossing faster, flatter, and capable of carrying the weight modern Europe actually moves. But the spirals inside the mountain above it are the record of what it actually took to get there first. Geometry pressed into service, where straight lines were simply not available. and engineers who understood that the only way around an impossible descent was to keep turning until the mountain ran out of reasons to say no. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.